Welcome back, Physics 20s, to our next lesson and our last lesson in Chapter 6. This is 6.6, and we're going to be looking at power. Now, the word power, I think, is used often in just conversations and lots in movies.
If you only knew the power of the dark side.
This gives you power over me?
Like those clips. But today we're going to look at what does power mean when we're talking about physics. And another place you may have heard the word power is when you hear the word horsepower, and this is often used to describe maybe the power of a vehicle or something like that. And horsepower is a unit, and it's related to another unit. 1 horsepower is equal to 745.7 watts. Now, watts might be familiar as well if you think of like a 60-watt light bulb or something like that, and this may have been heard in some other science courses. So if we take a look at watts, which is a measurement of power, watts is equal to how many joules per second. Now, joules we've seen before from previous lessons, and this is amount of energy, and seconds is amount of time. So power is going to be looking at how much our energy changes. Remember that triangle means change. So change in energy over time. So previously in all the other lessons, we were looking at how much energy there was. We were calculating how many joules. But now we're not just interested in how many joules, but how fast that energy is changed, so in how much time. So say that you can increase your kinetic energy to 100 joules. Does that happen in 1 second? Does it happen in 5 seconds? And if you're able to change the energy quickly, it's said to have a high amount of power. So power is defined as the rate at which energy is changing. If you have a high power, you can change energy quickly. If you have low power, it takes a larger amount of time to change that same amount of energy. Now, this isn't too much new material because we've looked at calculating a change in energy a lot before. We looked at the equations with energy potential of a spring and of gravity and of kinetic energy when calculating how much energy there is with these equations of half kx squared, mgh, and half mv squared. But then we also looked at change in energy is the definition of work. Work is a change in energy, and our other equation for that was work is equal to force times distance. So we have a lot of ways that we can be calculating this change in energy. Now we just have to divide it by time. So I'm going to do lots of examples of places where we can apply this concept of power to different scenarios. So the first one, let's say we have a stopped car, and then the car speeds up to moving. It's increasing its amount of kinetic energy. Let's say it starts with 0 joules of kinetic energy, and then it goes up to 400 kilojoules, that's 400,000 joules of energy, and then it gives us the time that happened in 7 seconds for it to speed up to this amount of kinetic energy. And then it says, what is the power of the car? So we said from before that power is equal to the rate that our energy changes. So it's our amount of joules, or energy, I'm going to put the change there, divided by our amount of time. And if we're looking for watts, this is going to be joules and seconds. So if I look at here, 400,000 joules, I'm going to have to write that not as 400, but 400,000 joules. That's how much the energy changed in 7 seconds. That's in the right unit already. Seconds. And I'm getting a number there of pretty big number, 57142.857. Really long number. Let's round that to 2 digits based off the 7.0 seconds. And I'm getting 5.7 times 10 to the 4 watts. All right. That could be also 5.7 times 10 to the 4 joules per second. All right. Same thing. Watt is equal to a joule per second. Okay. So not too hard. Just look at the change in energy divided by time. Let's look at another example where now we have a crane and it's going to be lifting a mass up off of the ground. The question says a crane lifts a 1,000 kilogram mass 10 meters in 20 seconds. What is the power of the crane? Okay, so same start. We have that our power is equal to our change in energy over time. This time it's not gaining kinetic energy, but when it raises off the ground, it's gaining potential energy. And this is potential gravitational that we calculate with mgh. So I'm going to plug that in up there, and we'll take our mass, which was 1,000 kilograms, times by g, 9.81 meters per second squared, times by the height. It said it went up 10 meters. So that's the energy. And then we divide by how long it took to change that energy, which is just 20 seconds. Sorry, in seconds, which is good. And when I put those into the calculator, I'm getting a number of 4,905. All right, let's round that to 4.9 times 10 to the 3. This was joules divided by seconds, which is watts. Now, because this is times 10 to the 3, or it's like 4.9 thousand, we could also write that as 4.9 kilowatts. We can use that prefix of kilo to mean thousand for watts as well. So there's an example with potential energy gravitational, and we'll take a look at another example. In this case, we have an athlete pushing a weighted sled. This is a training method working on explosive power and strength, and it says an athlete pushes a weighted sled with a force of 220 newtons for 10 meters. She completes this in 4.5 seconds. What is the power of the athlete? Okay, so this is asking for power. I have to start with that same equation of P is equal to change in energy over time. But this one isn't as clear to calculate that amount of energy with what we were using before, like the EP or EK. It is gaining kinetic energy as it starts to move quickly, EK, but to find that I would need half mv squared. It doesn't look like I have the mass, and it doesn't look like I have the velocity. So half mv squared doesn't look like it's going to work for this one. But fortunately, if you remember from the slide earlier, we also know that change in energy is the same as work. And work is also equal to force times distance. And in this question, they give us information about force and the information about distance right there. So we should be able to still solve for this change in energy by using force times distance. So we're going to plug in the force there. She applies 220 newtons, and that gets times by the distance of 10 meters. Okay, so that's the amount of energy change. That's the amount of work that was done. So those are the same thing. Work is equal to a change in energy, and it's completed by or divided by 4.5 seconds. And I'm getting an answer there of about 488.8 repeating. We have two digits in the question from the 10 meters and the 4.5 seconds. So we'll round this to 4.9 times 10 to the 2. What's that? Times 10 to the 2 watts. If we wanted to put this in kilowatts, it'd be 0.49 kilowatts, which would work as well. Now, I'm just going to point out in this person, it was asking for the power of the athlete, which is what we calculated because the athlete applied a force of 22 newtons for 10 meters. We can't necessarily say that that would have been the same as the EK of the sled. Now, the reason that is because there could have been friction. And so just to imagine, it didn't say anything about friction in this case, but imagine if the friction was negative 220. So if we had the box here, she's applying 220 and friction is applying 220 backwards, all right? She's still doing the same amount of work. She still has the same amount of power. She's applying that force over that distance. Our calculation would be the same. But if the friction is working back in this direction, it's just going to be going in that constant velocity the whole time she pushes it. So it's not going to be gaining that amount of kinetic energy as the same amount of energy she's putting in. It's all turning into heat if our friction is the same number. So I don't see that that would come up in questions where it's asking really the difference between those two. But if you're wondering, well, if I was given the speed, could I just calculate it there? You could calculate the power that was like applied to the object, but to figure out the output of the athlete, the actual amount of power that she did, the energy that she used, and the force and the distance, we would use that formula there because that was the power output of the person. Now, it wasn't as efficient of changing the amount of energy if there was some friction, but we did accurately calculate the power of the athlete. So I hope that makes some sense, the difference between those two. Again, not sure if you'd see a situation like that, but knowing that those could be different due to friction. But this one, we were assuming there was no friction. We're going to take another one where we do assume that there is some friction. So a car is traveling at a constant velocity, 25 meters per second, and there's a force of friction and wind resistance of 400 newtons. What is the power of the vehicle? Okay, so the vehicle is moving along at 25 meters per second. We're trying to figure out what the power of the vehicle is. Let's start the same way. Power is equal to change in energy over time. Okay, now you think, well, change in energy, this says we probably think we go to EK is equal to half mv squared, but it's going at a constant velocity of 25 meters per second. Remember this triangle here, it means change in energy. If you're just going at a constant velocity, it's not really, the car isn't increasing its speed at all. So there's nothing going on there. Kind of like we were talking about with the athlete last time, the change in energy of the weight compared to the amount of work the person is putting in could be different, and we're going to see that here. So is the engine doing any work? Well, it's got to be, because there's friction and air resistance that is applying a force of 400 newtons. So I'm going to draw this from the car here, going backwards, and say there's 400 newtons. I'm going to make it negative, going back on the car like that. If the engine was turned off or doing nothing, this would be decreasing, right? So the engine is doing some work. It is supplying some power to the car. But how can we figure that out if the velocity is staying the same? Well, we look at our other formula. We said change in energy is also equal to work, which is force times distance. So let's put that in there. Force times distance divided by time. And I think, well, I still don't really have the distance and it didn't tell me a time. But what we're going to do here is notice that this is force times d over t. And if I circle that part right there, we've seen that d over t is equal to velocity. So if I sub that in, velocity is equal to distance over time, I can now say that this is equal to our force times by our velocity. And all of a sudden we have enough to solve this equation, because we know the velocity that it's traveling at, and the force, we just have to look at a free body diagram. If only force was negative 400 newtons, this would be slowing down. To be going at a constant velocity, there must be force of the engine pushing this way at 400. So the engine is doing or applying a force of 400 newtons, and it's keeping the vehicle at 25 meters per second. So then we take our 400 newtons times by our 25 meters per second, and we should get our answer just like that, which I'm getting a number of 10,000 watts, and so this would be 10 kilowatts for our answer. Okay, so it seems like it gives you very little when it just gives you force and it gives you speed, but if we use this equation that power is equal to force times velocity, which I think is on your formula sheet, we can just put those two together and get our answer. So that gave you kind of 4 different scenarios where you can calculate power. So hopefully that helps you with the practice questions and the unit test that will be coming up right away. Let me know if you have any questions, and I will see you in the next unit.